thin shell of mass m and radius r, we know what is the gravitational potential when the point of interest lies outside this shell, on the surface and within the shell. At a point which is outside the shell, that is Vc, potential of point C, is for that we assume the whole mass to be concentrated over here at O, and the distance we take it as R2, so it comes out to minus Gm upon R2. To find the potential at the surface and within this shell, it is same. Whatsoever is the gravitational potential at the surface, same is within the shell, and that is equal to minus Gm upon R. That is, we assume the whole mass to be concentrated at center, and we find what is the potential at the surface, that comes to minus Gm upon R. Whatsoever is the potential at the surface, the same is going to potential within this shell. So far we have been considering a thin shell whose thickness is almost equal to 0. But what if this shell has some thickness? That is, we have an inner radius small r and we have a capital radius capital R. So this shell has this much thickness. R minus R is the thickness of this shell. We are interested now in finding what is gravitational potential, let's say at the inner surface or at the outer surface, or let's say the points beyond this, and what is the potential inside this shell. So for that, we shall be making use of the concepts which we have understood over here. This shell of this thickness is comprised of many such concentric shells of very minute thickness. A shell, a thin shell, plus a thin shell, plus a thin shell, plus a thin shell. So obviously we can get a thick shell. We are interested now in finding the gravitational potential because of this mass, number one, at the inner surface or within this cavity, and at the outer surface. These 2 points, they are our points of interest. Subsequently, we shall also be finding the gravitational potential inside a solid sphere also. But right now, our consideration is number one, a shell which has a thickness, considerable thickness, and second is we are trying to find the gravitational potential at the inner surface or within this cavity, and second is at the outer surface. Obviously, if the outer surface we have to find out what is the gravitational potential, we can assume the whole mass to be concentrated over here, and this capital R is the distance, so directly we can use minus Gm upon R, that is we can come to this. But let's get to the same answer using the basic principles of integration. So over here, whether we have to find the gravitational potential at the inner surface or at the outer surface using the principles of integration, we shall also be making use of our earlier understanding of the gravitational potential in case of a shell, that is how we found out within the cavity, outside the cavity, and at the surface. To find the gravitational potential at the inner surface of this shell of radius small r or within the cavity, what we do is we consider a very thin shell of thickness dx and radius x. Now what we shall be doing is we shall be making use of our earlier understanding, that is, if there is a shell, there is a thin shell, and if we have to find out what is the potential over here, and that is at a point which lies outside this shell, so we assume the whole mass to be concentrated over here, and we directly say the potential over here is minus Gm upon R. And if we have to find the potential at the surface or within this shell, then what we do is we find the potential at the surface. Whatsoever the potential at the surface of this thin shell, the same is going to be its contribution within this shell only. So at x thickness dx, we consider this shell. Now if the mass of shell is capital M, outer radius is capital R, and inner radius is small r, and we have considered at distance x a very thin shell of thickness dx. So first we find its mass. So 4 pi x square is the surface area of this shell, and thickness is dx. Area into thickness, area into height, that is a volume. So this stands for volume. Volume to density is the mass. Mass of what? Mass of this shell in red color, because density is mass by volume. We take it as differential element of mass, that is dm. Now if we are interested in finding the gravitational potential at the inner surface or within the cavity, that is, it is going to be minus g dm, that is dm is obviously going to be same, it's going to be this much only, differential element of mass. And if we are interested in finding what is the gravitational potential at the inner surface or within the cavity, then obviously we find the gravitational potential because of this red shell at its own surface, and whatsoever is within this, it's going to have the same contribution. So it is going to be minus g dm by x. X is the radius of this red shell. So whatsoever is the potential at the surface, the same is going to be contribution within it. So minus gm, so minus g dm upon x. So this is one point. Second is, in case we have to find what is the gravitational potential at the surface, then over there what we do is we assume the whole mass to be concentrated at the center and we say g minus gm upon r. So if we are interested in finding the gravitational potential at B, then what we say is it is going to minus g dm upon this going to be r. Whereas over here, when we are finding within this, it is going to be x, rest is same, minus g dm upon r. Obviously, if you have to find the gravitational potential at the surface, we can once again directly assume the whole mass to be concentrated over here and minus gm upon r, that should be the answer. But over here what we are doing is we are using integration to get to the same answer. So now we are doing two things. One is we intend to find what is the gravitational potential at the inner surface or within this cavity, and the second is what is gravitational potential at the surface when the mass of the shell is capital M, inner radius is small r and the outer radius is capital R. So one is minus g dm upon r, that is to find the potential at the B, that is outer surface. And if we have to find what is the potential at the inner surface in the cavity, we use minus g dm upon x. That is, we find the surface, the same is going to be contribution. Rest is a simple integration, that is we shall be using over here. So for this, when we have to find the surface, minus g dm upon r, this is differential element of potential contribution. So the total potential over here is integral of this, and x is going to be variable, x is variable, x is going from where to where? X is, the inner shell starts at x is equal to r, small r, and the final shell, outermost shell is at x is equal to r. We do the integration and over there we find Vb is equal to minus gm upon r. That is the answer which we could have directly got if we assume the whole mass to be concentrated over here at the center, and obviously at a distance capital R, it is going to be minus gm upon r. So this is in consonance with what we had expected. Now finding the gravitational potential at the inner surface, at this surface. So what we do is minus g dm upon x. What is dm? Differential element of mass of this shell. It is once again 4 pi x squared dx into rho. We put the value over here. So rest is all very simple steps of integration. Density is mass by volume, mass upon volume. Volume is of this shell, that is total volume minus this volume of cavity, that is 4 by 3 pi capital R cube minus 4 by 3 pi r cube. We get the volume of this shell. So mass upon volume is density. We have replaced density by mass upon volume. We put it like this. So this comes, x is variable, x is once again going from small r to capital R. So this is the potential at the inner surface or within the cavity of shell of mass capital M, whose internal radius is small r and the external radius, that is outer radius, is capital R.